We just watched a video where somebody fires a rifle, the bullet is propelled forward by the explosion, the gun is propelled backwards by the explosion. We know that the momentum of that gun slash bullet before it was fired was zero. You guys told me that. The gun and bullet were both at rest. But yet, the momentum of the bullet after it's fired is not zero. It's something. Let's say it's 500 forward. What's the momentum of the gun backwards? 500. Negative 500. Because the total momentum of the gun slash bullet has to remain the same. You can't gain or lose momentum. If it was zero before the explosion of the gunpowder, then it had to be zero after the explosion of the gunpowder. We say in an isolated system, the total momentum will always remain the same. That's the law of conservation of momentum. Another way to say that, momentum can't be created and it can't be destroyed. It can be transferred from one thing to another, but it can't be created and it can't be destroyed. What do we mean by this, by the way? It's italicized, so it must be important. In an isolated system, we don't gain or lose momentum. It always has to remain constant. You guys remember from Science 10 what that means? 2 years ago? An isolated system is a system that nothing's coming in or out. Specifically, there's no external forces. No external forces. What do we mean by an external force? Well, maybe friction is an external force. Maybe wind is an external force. Maybe if you're talking about the collision of two cars, maybe a third car comes into the mix here. When we have no external forces, the total momentum will always remain the same. So what do you do if you have an external force? Make the system bigger. Make the system bigger. Account for that external force. If a third car enters the mix, well, then don't just analyze the collision between the two cars. Analyze the collision between the three cars. If there's external forces, make that external force internal. Make the system bigger. In an isolated system, the total amount of momentum will always remain the same. Now, when are we going to use this? When is this useful in solving problems for us? Well, when we have what we call a collision, which is, I think, pretty self-explanatory, when two cars hit each other, collide, or two football players collide, or two asteroids collide with each other, when anything hits something else, that's a collision, and the law of conservation of momentum applies. The term explosion is a little bit less literal. We might mean literally an explosion of a bomb, or we might mean something a little less literal, like maybe the explosion of a gun. Bullet goes one way, gun goes the other way. Or even less literal, the explosion of you and a ball. You're standing on ice, you throw a ball, the ball goes forwards, you go backwards. When one object becomes two, we think of that as an explosion. And whenever we have one of those explosions, we can use this new law that we just learned to analyze it. Now, we've been talking for the last several days about this concept of impulse, which we defined as change in momentum. Explain something to me. I don't get this. If momentum always remains constant, how can we have a change in momentum? If the momentum doesn't change, then how can the momentum change? Matt, you got an answer for me there? No? Okay, sometimes it could be. Yeah, sometimes it could be. Momentum could be transferred to something surrounding it. Yeah, could be transferred to the earth. I drop this pen on the earth, the pen stops, right? Well, the momentum is transferred to the earth in that case, right? Here's the deal, though. When we're using conservation of momentum, we're analyzing a system. Look at here. In an isolated system, momentum will always remain the same. When we're looking at all of the objects within the system colliding or exploding, okay, momentum always remains the same. But conservation doesn't mean nothing ever changes. Conservation means the total amount never changes. So if you've got a collision between two football players, the total amount of momentum will remain the same. But one football player can very easily gain momentum. What happens to the other football player? Was your hand up? No? What happens to the other football player if the one guy gains momentum? The other guy's got to lose momentum. Okay? Impulse experienced by both of them, but the total amount of momentum remains the same. So here's the deal. When we're analyzing a system, we're going to use conservation of momentum. If we're analyzing individual objects within the system, we're going to use impulse because the system has momentum remaining the same, whereas the individual objects will experience a change in momentum. One guy gains, one guy loses. So how exactly do we write this? Well, before I write anything down on this, let me take you back to the concept of impulse that we did last week. Impulse, if you remember, we derived from Newton's second law, F is equal to m times a. That's where impulse comes from. In fact, that's really what impulse is. When we define Newton's second law in physics 20 as F is equal to m times a, that's not the way Newton said it. Newton talked about his second law in the context of a change of momentum. We just didn't know anything about momentum in physics 20, so we couldn't talk about Newton's second law that way. We couldn't talk about it the way that Newton actually stated it. But it's the same thing. It's just a bit of a different way of saying it, that's all. Well, the law of conservation of momentum comes from Newton's third law, not his second law. And Newton's third law, if you remember from physics 20, says if object A applies a force on object B, or let's say object 1 applies a force on object 2, then object 2 will always apply an equal and opposite force on object 1. There will always be an equal and opposite force. You guys remember that, right? That's the one you learn in grade 7 that says for every action there's an equal and opposite reaction. I told you guys that I had in physics 20 last year. I don't like saying it that way. For every action there's an equal and opposite reaction. I like to think of it as object 1 applies a force on object 2. Object 2 applies the equal and opposite force on object 1. Well, let's replace F with m times a. That means we're going to say m1 times a1 equals negative m2 times a2. ma equals ma, but opposite direction. And now let's make one more quick substitution. Replace a with delta v over delta t. So m times delta v1 over delta t1 equals negative m2 delta v2 over delta t2. You guys okay with those substitutions right now? Okay, watch what I'm going to do here. I'm going to cross off the t's. How come I can do that? Can anybody explain to me why I can do that? If t appears in both terms, I can cancel them out, right? But they're two different t's, t1 and t2. How come I can cross those off if they're two different terms? Yep. Good. Good. If object 1 collides with object 2 for a half a second, then object 2 is colliding with object 1 for a half a second. Even though the times are called something different here, the times are going to be exactly the same values. So we can get rid of them. That leaves us with m times delta v, m1 times delta v1 equals negative m2 times delta v2. What does that tell us? The impulse of object 1 is equal and opposite to the impulse of object 2. In other words, object 1 gains momentum, object 2 loses momentum. But we're not quite done there. We're going to replace delta v with v1f minus v1i. And we're going to replace v2, delta v2, with V2F minus V2I. And finally, I'm going to skip a couple rearranging steps here now because the point of this is not the algebra and the mathematics, but rather the final product. If you're troubled by the step that I skip, just let me know and I can work through it with you, okay? When we rearrange this, when we distribute the masses inside the brackets, both mass 1 and mass 2, and rearrange it, we end up getting something that looks like this. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. What does this tell us? The momentum of object 1 and 2 combined equals the momentum of object 1 and 2 combined after the collision or explosion. In other words, the total momentum before the initial momentum equals the total momentum after the final momentum. This is the law of conservation of momentum. The total momentum before equals the total momentum after. And we're going to use this, what you see circled in red there, we're going to use this from now on every time we see a collision between two objects or whenever we see an explosion or something like an explosion. You know, throwing the ball on ice, it goes forward, you go backwards. Okay, something like that, we'll use whatever you see circled in red there. So let's put it into action here. Example 9.6 on 477 says, a wooden block attached to a glider has a combined mass of 0.200 kilograms. The block and the glider are at rest on a frictionless air track. A dart gun shoots a 0.012 kilogram dart into the block. The velocity of the dart system is afterwards is 0.78. What's the velocity of the dart just before it hit the block? This is a little bit confusing, eh? We have to get used to that. Okay? If you talk to anybody from first semester about the diploma exam, okay, some people said it was okay. Some people said it was hard. But everybody said, man, the reading that you had to do. There was multiple times when you saw an entire page of information for one question. And sometimes the reading was just difficult to wrap your head around. There's not nearly as much reading in this question, but I think this one's kind of hard to wrap your head around, actually. You got a block attached to a glider that has a combined mass of 0.2 kilograms. All right, let's draw it. Okay, let's draw it. That's a strategy we can follow. Let's draw it. Here's my block, and here's this little glider. The block and the glider have a combined mass of 0.200 kilograms. They're at rest. The block and the glider are at rest. So we're going to say its velocity is 0 meters per second. They're at rest on a track, on an air track. An air track, by the way, is this apparatus that pumps air out these little holes to create this cushion of air for the glider to float on. It's kind of like an air hockey table. You guys know when you play air hockey, the pucks just float on the cushion of air? These gliders float on this cushion of air, which reduces friction to effectively 0. Okay, they're at rest. Now what are we doing? Oh, we're firing a dart into the block. Here's the dart. Going this way. We know that the dart has a mass of 0.012 kilograms. We don't know how fast it's moving. That's what we want to find, right? How fast is that dart moving before it collides? And then the dart sticks to this block. So afterwards, it's going to be over here with the dart inside. Okay, so this is initial. And this is final. Does the setup of this kind of make sense? We've talked since the first day of class here how we're not just looking at givens now, we're looking at the situation. Okay, I think we've described the situation by this diagram. Look, this is a collision between the dart and the block. Anytime we have a collision, we can set PI equal to PF. So let's do that. That looks like a PF equals PF. PI equals PF. So the initial momentum equals the final momentum here. We're going to say the initial momentum consists of momentum from two different objects. That's the dart. We're going to call that object number 1, and it has a momentum of m1 v1I. Mass 1 times velocity 1 initial. But it also is made up of the momentum of the block slash glider. The block and glider are together, right? And they stay together the whole time. So we're going to treat those as one object. We're going to call them object number 2, m2v2I. Now, after the dart collides with the block, how many objects do we have? Look at the picture. How many objects do we have? Somebody said it. 1. It's the block slash glider slash dart. We're going to call that MVF. Why not M1 V1F? Well, because it's mass 1 and mass 2 combined. Sometimes we might call it M12 to remind us that it's both of them combined, or we can just call it M. 2 objects before the collision takes place, 1 object after it takes place. 1 object is made up of the dart and the block and the glider. All right, M1 is 0.012 kilograms. V1I is, that's what we're looking for, right? The velocity of that dart before it hits. M2 is 0.200 kilograms, and V2I is 0. Oh, look, if V2I is 0, we can just cross that off, right? We don't even have to put that term in there if we don't want to. M, the combined mass, is 0.212 kilograms. It's the dart and the block combined because the dart is stuck inside the block. And VF, we're told VF is, oh, look, we do this backwards, didn't we? We do everything to the left, didn't we? Is that a huge deal? No, it's probably not a huge deal. Okay, let's just define left as positive so that we stick with the positives. Okay, do you guys understand what I'm doing there? I drew it wrong, but that's not going to change my final answer except the direction. If I get an answer that's to the left, it means it's to the right. DF we're going to say is 0.78. All right, let's do this as a group here. Let's say 0.212 times 0.78, and let's divide that by 0.012. Before we calculate that, tell me what you think V1I is going to be, small or big? The final velocity is 0.78. Do you think the velocity of the dart is going to be more than 0.78 or less than 0.78? More. How come? How come it's going to slow down though? Tell me what about the block slows it down? Yes. The momentum of the dart before the collision is the same as the momentum of the dart slash block slash glider after the collision. Same momentum. But if it's the same momentum and the block slash dart slash glider has more mass, it's got to have less velocity, right? So you got to figure that dart is going to be moving faster, quite a bit faster probably, because its mass is quite a bit smaller. So we press enter here, we end up getting 13.78. V1I is, we're going to round that to 2 digits, 14 meters per second. Is that quite a bit bigger than the velocity of the block slash dart slash glider? Yeah. Yeah, quite a bit bigger. You can imagine how something like this might be useful as a police officer. You're investigating an accident scene. You measure the tire marks, the skid marks on the road to determine how fast things were moving after the collision. But wait, we can calculate how fast the car was moving before the collision. Why is that useful? Because it might be useful to know whether the guy was speeding or not before he collided, right? So we do almost the same calculation if we're analyzing that accident scene. Does that make sense? All right, let's take a look at those two questions, please, on page 477.